here, okay, we are looking for the highest and the lowest MJ, okay, quantum number. So I can here select this. Okay. I can here select this row. So we have here the lowest MJ, okay, -2, and the highest one is for +2. Okay. Next, we between these two values, okay, -2 and +2, we can have +1, -1, and 0. Okay. If we write, okay, for the MJ, okay, we know the MJ here. So the lowest value is -2. So next we have here
Excuse me, doctor.
yes.
Can you record the class?
Okay. Okay, next we can select this, for examples, +1 and -1 MJ. Okay, +1 and -1. And also, we can select also here the 0. Okay. So from here, what you can see here, okay, the M and the MS here. The M here is between -1 and +1. Okay. MNS, okay, as well is between -1 and +1. So we can have here all the M value here is from -1, 0, 1. And most of the MS is from -1, 0, and 1. Okay. So this one will give 1. Total orbital angular momentum and the total spin angular momentum, okay, here is 1, and the J is 2. Okay. This will give triplet P2. Similarly, you can do for the, okay, now what here left for the MJ, the quantum number MJ is the negative 1, okay, and positive 1. So X, the lowest one is negative 1, and the highest one here is positive 1. So you can select this one. Okay, in between, okay, is 0. So we have here another MJ is negative 1, 0, and 1. Okay, so this will give J1. So we want to find the M, okay, the component of total orbital angular momentum, and the MS, the component of total spin angular momentum. So the M here, okay, also between negative 1, okay, and MS also is from negative 1 to positive 1. Okay. So from here we can write, okay, you can try this out. Okay, the singlet P2, the triplet P1. Okay, you also can do for triplet P0. Okay, by here choosing this one. Okay, okay, so we can have here also for the triplet P0. Okay, and we have also here this one, and this one. Okay, these 3 rows will give MJ is negative 1 to positive 1. It will give J is 1. Okay. So MS0, 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 this will give singlet state, and the M here is negative 1 to positive 1. gains. Okay, this will give singlet P. Singlet P1. Okay, with this Mj is from -1, 0, and 1. Okay. So you also here, okay, can use these tables to get the all possible term symbols for this electronic configuration S2P. Okay, for the non-equivalent electron, okay, we can use directly the angular momentum addition rules. Okay, like this example for 1s2p. Okay. For the non-equivalent electrons, normally we will use this angular momentum addition rules to find the atomic term symbol. Okay. How about for the okay, so this is the 1s2p. Have here singlet P1, okay, triplet P0, triplet P1, and triplet P2. For the equivalent electron, okay, so this again is for the non-equivalent electron, okay, with different n here, n, s, and n prime s, like 1s to s. Okay, you can get here 4 rows when here constructing these tables. Okay, this is for the non-equivalent electron. We have here another examples. For the equivalent electron, okay, like in these closed shells orbitals, okay, we only can have here 1 rows. This is for the equivalent electron. Okay, at the same time, these 2 electrons are closed shells electron. Okay. Okay. Now we have done, okay, discussing this closed subshells electrons, closed the non-equivalent electrons. Okay. The last one here, already here introduced, okay, the equivalent electrons like 1s2, 2p6. Okay. We can also have the another example here, the np2 electron. Okay. Here for the equivalent electron, you must use these tables. Okay, you cannot use the angular momentum addition rules, because when you use the angular momentum addition rules, you can get all possible quantum number with same set of m quantum number and the ms quantum number. Okay, like in these examples, we have n quantum number, same n quantum number for these 2 electrons. So if we use the angular momentum addition rules, that means we can get, okay, some combination of quantum number will be the same for these 2 electrons. Okay, so we cannot have the same set of quantum number for 2 electrons. Okay, so we must use these tables, because from this table you can identify, okay, like here, you cannot have here positive 1, positive 1, positive half, and positive half here. Okay, you cannot have this. Oh my God, what is this? Okay, positive 1, because we have this same n. Okay, NP. You must have at least one quantum number here. At least one quantum number is different. At least one. So the one quantum number here is positive half and negative half. Yeah, it cannot be here positive and positive and positive half. So for the MP2 here, you also can, okay, get the term symbol from this table by eliminating here row by rows here. Okay, to get this term symbols. Okay, you can try out this one. Okay, we can compare this with non-equivalent electron here. Okay, okay, this typo here. Okay, this should be n prime. Okay, you can have same m for this electron, because have this different n. Okay, add this one here. Okay, which in this case is n quantum number, n prime. Okay, so what you can see here, for the equivalent electron, we have here 1, 2, 3, 4, 5 atomic symbols for NP2. Okay, for the non-equivalent electron, we can have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So from the non-equivalent electron from non-equivalent electron to equivalent electron, this number of term symbol here, okay, is reduced from 10 to 5. Yes, because we have ignored some of the combination of the number having same quantum number, same set of quantum number for these two electrons. Okay, that's why here. So for the equivalent electron, the number for the equivalent electron here is actually subset to this number for the non-equivalent electron. We have 10 here, we have reduced to 5. Okay, now we have done for this topics, the term symbols. Okay, I have here listed, okay, the equivalent here. This is closed shells and also the equivalent electron. Okay, like this P2, like this P4. Okay, all equivalent electrons and non-equivalent electron like this one. Okay, pp. Oh. SD. Okay, if you have a mixture of this equivalent electron here, 3 equivalent electron, plus with this non-equivalent electron in S and 3 electron in P, they are, okay, of course, they are non-equivalent, okay, because they have here different and probably same N to S, let's say to S, but different L here. Okay, so we have here at least one here is different, which is the M quantum number, M for L. So we can treat this separately to find the term symbols. So for the non-equivalent electron, for the equivalent electron, we have this one. Okay, normally, okay, in your exam, this table will be given. Okay, sometimes this will be given. For the P3 electron, we have this SDP term symbols. So you must know how to use these tables. You must know how to use this table. Like here, given this electronics configurations of this mixture of non-equivalent electrons, 1 in 1s, 3 in p, 1 in 2s, 3 in 2p. So you can treat this separately. Here the P3 have these 3 symbols, and also, okay, we can find this easily for this 1 electron. Okay. There's no S1 here. Okay. Okay. S1, only 1 electron here. You can get this doublet. 2 half plus 1. Okay, you get doublet. So S. So now you can have here from here. Okay, you can figure out the L is 1. The S is half. This one. The S is half. The L is 2. So this one. So this one is what? L cos is 0. S is 4. This is 2. S plus 1 is 4. Okay, 3 half. Okay. This one. So from here, okay, this we know. L is 0. S is half. So you can combine here all the quantum number here. This one, this one, this one. Using angular momentum addition rules. Okay. This with this one. This with this one. This with this one. Okay. this with this one with this one to get these term symbols. Okay, you also can try this. Okay, try this out. Okay, to get 1, 2, 3, 4, 6 atomic term symbols. Okay, using the angular momentum addition rules. So the Hans rules here, okay, applies for the ground state configuration. 1s for helium, for lithium 1s2, 2s, but occasionally here fail for the excited configuration. Okay, for the 1s, 2s, sometimes we cannot use these Hans rules. Okay, so like here, for terms arising from the same electronic configurations, the terms with the largest value of S lies lowest. Okay, you can refer this tables. I forgot. S, okay, the largest spin multiplicity. Okay, even though this is the excited electronic configuration, this is not the ground state electronic configuration. Okay, we also can apply this. So this is the largest spin multiplicity, lies lowest energy. Okay. Okay, if there is more than one terms with the largest S, then the term with the largest S and the largest, okay, the largest L lies lowest. We have same P. Okay, so this second rules doesn't here apply for this triplet P and singlet P. Okay, we have this same P. So if the state have the same value of L and S, like this, same value of L and S, okay, for a subshell that is less than half wheel, 1s 2 feet here, 2p here is less than half wheels. The state with the smallest, okay, supposedly J value is most stables, lying the lowest, okay, meaning that lying the lowest state. So this, okay, supposedly here, lying the lowest state. Okay. But this is not the case, like here. Okay. We have here triplet P2. The highest J here, okay, lies lowest state. Okay. So this third rule here fails to, okay, explain this triplet P2, okay, is the lowest state. Because of what? Because this is the excited electronic configuration. Sometimes fails, okay, we fail to use this, okay, this rules fails to explain this, okay, the order of this energy, P2, P1, and P0, okay. Okay. Now, okay, you can see this. Okay. In your exam, okay, sometime I can take any plot or diagram in this dot. Okay. Like these examples for the carbon atoms. Okay. The core electron here, 1s2. Okay, we have these two. The core electron is always closed shells. We can ignore this one. Okay. This always will give singlet S. Okay. Where L is 0, S is 0. When we combine with another quantum number here, is S2 to P2. Okay. This L0 and S0. Okay. Do not actually change the last quantum number, total quantum number for L and S. Let's say we have here this combination 2p6, 1, 2, 2p, 6, 3d1. Okay, you can ignore this one. This closed shells is always L0, S0. Okay. What you need here to consider is only this open shells orbitals. Okay, only this D1. So this overall, this will give L2, you see, half here, 2 times half plus 1 double D. State. So this is the ground electronics configuration. This is excited here by promoting here 1 electron here to 3s, 3p, and here from electron s here to s to p here. Okay, you can see here. Okay, without the spin orbit interactions. Okay, the coupling between total angular momentums and the orbital angular momentums, you can get this energy diagram. Now, parity, okay, you can skip this one. Okay, you should learn this invisible one, the parity. Okay. Even and odd parity. So the eigenvalue for the 2 electron system for helium, okay, how we can mathematically find the eigenvalue, like here, okay, for this 2 electron spin, okay, half and half. Of course, here, this is half and half. The M, oh sorry, the MS. Okay, so the total spin here, okay, if you draw the vector diagram, so this is half, so this is half. H bar, this will give the H bar. Mathematically here, okay, can be proven here. So this is H bar. Okay, we have these 2 components of operator. One is for electron 1 and 2. Electron 1 here acting on this electron 1 only. Electron 2 here on this 2 only. Okay. You learn in physical 1. This operator, this is the eigenfunctions. So electron 1, 1. So we get, this is the eigenvalue of H bar. Okay. S1 Z alpha 1. So you'll get this eigenfunctions and the eigenvalue. This one. You get back this one. And this as well. For the electron 2. Okay. So now we have this one. We have proof. You can also compare this with this vector diagram for angular momentum. Okay, we use these properties you learn in physical 1. You also can do for this spin to electron spin, beta beta, beta alpha plus beta alpha, here minus beta alpha. Okay, and using this property you learn in physical 1. Okay, alpha here is the eigen functions for the S square and the SZ. Okay, so this is the eigen function. Sy operator. Okay, the alpha and beta are not the eigenfunctions for this x components of spin vector and y component of the spin vector. So this is not the eigen function. Okay, so you can prove this using this property. We can have this. Okay, what you can see here, both here, okay, what you can having here same orientation of spin, negative half. So you get this net vector here will be negative. Okay, this negative typo here. Okay, this is positive. Oh, sorry. This is the not the SZ. Okay, the S square. S square. Okay. So the SZ here, this one. Okay, negative. The net vector here, negative. Okay, negative half. Okay, and also this vector, both here, positive half. Okay. Okay, the SZ here is 0 here. Okay, we can have here same contribution from the alpha and beta. Okay, so the net vector here, the component of this vector is 0. Okay, so now you can have here this vector. Okay, with S here, one, and S here from positive to negative 1. Okay, so here S, this is the triplet state, this is the singlet state. Okay. Let me check here. Okay, the SZ here. Okay, sorry, for the S square here. Because the S square here, okay, so this one, we have S plus 1, S H bar, okay, this equals H bar square, okay. So we can have here S, okay, to be 1. This is SZ. Okay, so this is 1. For the 0, this one, okay, this is 0 H bar square. So S1, S H bar square. Okay, so S is 0. So this is the vector. Okay, to represent this alpha alpha, beta beta. Okay, these two vector, this is net vector. Okay, and also you can draw differently like this one. Okay, so this is S. Okay, and this one for the plus, this is for, okay, the minus 1 here. Okay, so this is the plus 1, this is the minus 1 here. The net vector here is non-zero here, okay, which is not 0. This is 0. Okay, now we are going to, okay, discuss the atomics Hamiltonian. Okay. So the Hamiltonian for atoms actually can be divided here into 3 parts. the zero order here, okay, in terms of perturbation theory, this is the unperturbed Hamiltonians. Okay. This is for the many electron atoms. This is the sum of the hydrogen-like Hamiltonian. This is the hydrogen-like Hamiltonian. And this H wrap, okay, you have seen this in previous lecture. Okay, the H prime here, the perturbation here, okay, we treat here as our perturbation. This is the interelectronic repulsions between electrons. All possible here. Interaction here, Ij. J here, okay, is higher than I. Okay, to avoid giving the same potentials, okay, like R11, R22. Okay, electron 1 with electron 1. Okay, that's why the summation index here, we use this J here. It's larger than I here, J, larger than 1. Okay, so this R1 to R, okay, if you have 4 electrons here, 3 electrons, so we can have here R12, R13, and this. Okay, because of this, we cannot have this R21, R31. Okay, so we have here R23. So, and also here we have the spin-orbit interactions Hamiltonian. Okay, our problem here, we want to find this energy. What approximation we are going to use given this Hamiltonian operator, spin-orbit with spin-orbit interaction. Okay, if we consider this one only, all the atomic state corresponding the same electronic configuration are degenerate. Okay, like 1 to S, 1 to S to P. Okay, we have seen this. Adding this one, okay, in the Hamiltonian operator, that we actually leave this degeneracy between state with different L and S. Okay, so different L here, or different S, or both here L and S. Okay, so that's here we actually splitting each of this configuration into terms. This one into terms. When we introduce this each repulsions, okay, next we add this. Okay, the energy split, okay, each term into here, into levels here. Okay, this level here compose this state with the same value of J. Here, same value of J. Okay, and this is 2J plus 1 for degenerate. Okay, corresponding to this different value of Mj. And we can remove this degeneracy of these levels by applying here external magnetic field. This is the Zeeman effect, actually. You learn in physical 1. So with this additional here terms in this Hamiltonian, okay, we remove completely here 2J falls the degenerate state into different NJ. Okay. Okay. Now we want to look this one. Okay. The spin orbit interaction here. This, okay. If, okay, we try to imagine, okay, like riding this electron in atoms. Okay. From our view of viewpoints, the nucleus here is moving around this electron. Okay, sorry. This nucleus moving around this electron. Okay. If we are on this electron, okay, riding on this electron. So what we can see here, okay, these motions of this nucleus produce a magnetic fields that interact with this intrinsic spin. Okay, this electron has intrinsic properties. The spin magnetic moments of this electron. Giving this spin orbit interactions. Okay. So the interaction energy from these motions and the intrinsic spin here. Okay. The magnetic moments M here with the magnetic fields due to this motion of this nucleus, we can write like this, the energy. These two vector, the dot product of this. And also we know the electron spin magnetic moments, these intrinsic properties of these electrons, ms, is proportional to the spin. This is proportional to the spin vector. Okay. You can refer in your notes, physical 1, the ms vector here. Okay. We can write in terms of electron G factor. You also can find this in spectroscopy. This is electron G factor. This M electron S spin. Okay, it's proportional to this spin vector. Okay. And the magnetic field here, okay, arising from these nuclear motions is proportional to the orbital's angular momentums, electrons' orbital angular momentums. Okay, so this is proportional to this orbital angular momentums. So the spin orbit interaction now, okay, we have these two vectors, S and L. Okay, these vectors. So the dot product of these two vectors depend on this orientation, relative orientation of these two vector, the L vector and the S vector. And we know from previous lecture, the J, the total electromagnetic angular momentum vector, is the sum of these two vector. Okay. Also depend on this relative orientation of these two vector L and S. Okay, and so the spin orbit interaction energy depend on J. Okay, so this is depend on J, quantum number. Okay, and you should know this one. Okay, the spin orbit interaction is a relativistic effect. Is the relativistic effect, and only can be properly derived using the Dirac relativistic treatments. Okay, so that actual atomic Hamiltonians